Go for it.
Yeah. Good evening, good afternoon, and good morning to all our friends attending from different parts of the world and to our speakers. This is our third plenary session. This plenary session contains two keynote lectures. The first one would be delivered by Professor Gopal Madhabushi and the second one by Professor Tauhata. This session will be chaired by Professor Swami Saran and co-chaired by Dr. Ramakrishnan. Before I hand over the session to our chair and co-chair, I would like to briefly introduce them. Professor Swami Saran is well-known personality. His book is very popular. Most of us all studied his books on soil dynamics. Apart from that, he has written several other books. Even till now, he's very active. He's still, I just came to know a few months back, he has completed another book writing. So for just sake of formality, I will just brief about him. Professor Swami Saran, Emeritus Fellow, retired from Indian Institute of Technology, Roorkee, obtained his PhD in 1969. He established teacher, researcher, and active consultant. He is the recipient of Coastal Research Award 4 times and IGS Award, including prestigious Kukulman Award and also awards from ISET, ISTE, and ISCMS. He has guided 29 PhD theses, 84 master theses, published 208 research papers, and 8 books. He has initiated research work on reinforced soil, analysis of foundation using constitutive laws, and dynamic analysis of retaining walls. He has provided consultancy to more than 300 projects of national importance. He visited the UK in 1974 under exchange program and IIT Bangkok as visiting professor in 1987. A national conference was organized at IIT Roorkee in 2007 to honor him. Considering his contributions, Indian Geotechnical Society conferred honorary fellowship on him in 2011. With this brief introduction, I welcome Professor Swami Saran to this session to chair.
Thank you, Ravi.
Thank you, sir.
Happy that you have given a chance to act as a chairman of this session in which two learned speakers are with us.
Yes, sir. Sir, let me also introduce our co-chair, sir, Dr. Ramakrishnan. Yeah. Dr. Ramakrishnan is currently working as a senior grade assistant professor at the Department of Civil Engineering, Amrita Vishwa Vidyapitham, Coimbatore, India. He is a PhD from the Indian Institute of Science, Bengaluru, and has extensively worked on geotechnical earthquake engineering, focusing on seismicity of Himalayas. His key areas of research include geotechnical earthquake engineering, slope stability, and soil stabilization. He has authored numerous research papers in peer-reviewed international journals and conferences, and is a reviewer for various international journals. He is a passionate researcher and has carried out relevant and impactful research at this young age, which was well received with about 200 citations. With this brief introduction, I welcome Dr. Ramakrishnan.
Thank you, sir. Namaste. Thank you for inviting me to co-chair this session. So I'm extremely honored to be here alongside Professor Swami Saran to chair this session. And I would like to extend my thank you to all the organizers. Thank you.
Thank you, Dr. Ram.
Yes, and now I request Professor Swami Saran and Dr. Ramakrishnan to take over the charge of the session. Please,
Thank you very much. Thank you very much.
Yeah, all right. So I would like to introduce the next speaker, Professor Ikuo Tauhata from the University of Tokyo. So Professor Ikuo Tauhata is a Professor Emeritus, University of Tokyo, and was distinguished visiting professor at IIT Bombay, India till December 2016. As a JICA expert, IIT Hyderabad in India till March 2017, and is the president of Japanese Geotechnical Society from 2014 to 16. And he served as the vice president for Asia, ISSMGE, 2013 to 17. His major fields of interest are deformation characteristics of cohesionless soils, dynamic analysis of earth structures during earthquakes, permanent displacement of ground caused by seismic liquefaction, soil improvement by densification and grouting, microscopic observation of granular behavior of sand subject to shear, and dynamics of landslide and debris flow, etc. Recently, Professor Ikuo Tohata worked on recovery and retrofitting for future of infrastructures on residential islands, river levees, and Fukushima #1 nuclear power plant that were damaged by the 2011 Tohoku gigantic earthquake, liquefaction, and nuclear disaster. Professor Ikuo Tohata has got more than 400 English papers in international journals and conferences, including a comprehensive book on geotechnical earthquake engineering. I would like to welcome Professor Ikuo Tohata. We are very glad that you are here today, and we are waiting for you to deliver your lecture. Thank you. Over to you, Professor Tohata. I think, sorry, I think you are muted.
Demuting. Okay.
Yeah.
Thank you very much. Thank you very much for your kind invitation. And actually, I missed the opportunity to visit India this time. I cannot go. I was thinking to first attend this conference and then go to Ooty and enjoy the toy trains in the mountains, but nothing is possible. So as a compensation, I have this nice cap. I got this one from in Pune. So I put this on as a compensation, this direction. Yeah, and then try to deliver this lecture. So let's share my presentation. Then start. Okay. You can see this picture, right? Okay, let's start.
Yes, sir. Yeah.
Okay, my title is the history of liquefaction mitigation technologies in the past 60 years. And I'm trying to show that the target of technology has been changing from time to time. Initially, the target was very relatively easy situations, but nowadays in the 21st century, target is much more complicated and difficult, and engineers have to be very careful about success of the project. So content is like this. I start with this overview of his history, damage. Then briefly, I'll talk about causative mechanism of liquefaction and principles of mitigation. Then mitigation measures for newly constructed structures. This is one of the easiest situations. However, there are two types of technologies. One is prevention of liquefaction. The second one is allowing for some limited extent of liquefaction, but without much damage. Then I will move on to existing structures. This is more complicated and difficult than new construction. And certainly the two technologies, one is just prevention, the other is allowing for limited extent of liquefaction. Then existing houses are very difficult target of technologies. And there are two groups. One is groundwater lowering, the other one is underground grid wall. Then I should briefly talk about emerging topics and miscellaneous issues. That's my idea. So overview of past damage was like this. Actually, liquefaction did occur many times in the history, in 1,000 years ago, 2,000 years ago. But in those days, liquefaction was not a disaster. It was just a phenomenon. However, human activities expanded into difficult soil conditions in the 20th century. So liquefaction changed from phenomenon to disaster. This is one of the earliest experiences in Niigata 1964. Maybe this is very famous as a tilting and falling down of apartment buildings. Certainly there is no good foundations under the building because sandy ground was considered good foundation soil in those days. However, liquefaction resulted in loss of rigidity, and there was no more bearing capacity in foundations. So this disaster happened. 1995 Kobe earthquake was like this. A harbor was destroyed by liquefaction and lateral movement of gravity key walls. So harbor operation stopped for 2 years. So this is an important example of business continuity planning. We should work not only on the safety factor, but also on economic aspects of disaster mitigation. And this is a measured acceleration, horizontal acceleration in the liquefied area. So top 16 meters was made of loose liquefiable sand. So within that 16 meters at the top, acceleration decreased drastically, as shown here. Both horizontal and vertical accelerations decreased drastically within this liquefied soil. Then 2011 Turk earthquake had magnitude 9. It was gigantic earthquake, and many things happened. This is one of them, floating of light underground structure. This building was actually a parking space underground, but this entire structure came up to the surface. And another phenomenon was the sand ejector or sand boiling here. This is evidence of liquefaction under surface. And this is enlargement. So you can notice that slope movement occurred like this. Maybe this movement is similar to circular slip movement. Slope moved downwards and the bottom part uplifted. So during liquefaction, groundwater pressure becomes very high and the effective stress is lost to 0. This means shear strength, sigma dash into tangent phi, becomes nearly 0. Therefore, slope moves like this. And recently, about 3 years ago, Indonesia suffered this astonishing disaster related with liquefactions. These 4 slope failures occurred like this, and lateral displacement was as much as 500, 600 meters in the horizontal directions. And many houses moved downslope, and houses were destroyed. And in those houses, more than 1,500 people are killed. So before this event, everybody believed that liquefaction does not kill. But nowadays, we have to say liquefaction kill people like this. And it was unbelievable that the slope gradient was only 2%. Yeah, in the past, liquefaction did happen in 2% slope, but displacement was limited to 5 meters, 10 meters only. So why 500 meters? Still, we don't know why. Is there any special conditions in this island or Sulawesi in Indonesia? This is a question. If there's no special things in this island, then liquefaction should have induced 500-meter displacement in 2% slopes in many parts of the world in the past. But it never happened in the past. So I still suspect there was something special in Sulawesi Island. And some people have been talking about the effects of irrigation canal. Okay, in the map, I show you 5 sites of lateral flow: Bararoa from top, Petobo site, and Rolla site, Jono Oge site, and the Shibaraya site. And there is an irrigation canal over here, and this is a picture. So this canal was not paved at all. So water was able to infiltrate into the slope, top of the slope. And some people say this water infiltration triggered 500-meter slope movement. This is a very easy idea. However, another one, remaining site, Bararoa site was like this. At the top of the slope, there is a residential area. There is no canal. This is important. So also, this is 6 weeks after the disaster, and headscarp cliff is dry. So this means that water infiltration is not the main cause of 500-meter lateral flow. Most probably, infiltration just increased the extent of lateral flow, but not the cause. It was not the causative mechanism. So why does liquefaction happen? This is a well-known problem. So essence of liquefaction damage is actually large ground deformation. Shaking is actually reduced by liquefaction, but the residual displacement deformation is the essence of damage. So because of large deformation displacement, serviceability of facilities is lost. But I used to say nobody is killed, but now I have to say many people may be killed, unfortunately. So this is a well-known mechanism of liquefaction. This is a loose packing of grains subject to horizontal cyclic shear stress. And grains falls into big voids like this, and water is pushed out towards the surface. So water pressure is pressurized and drained out towards the surface. According to the Darcy's law, water flow takes 30 minutes or longer to reach the surface. So in the meantime, water pressure is held high, effective stress is lost, and large deformation happens. So liquefaction is prevented or mitigated by changing the story shown above, shown here. So there are several kinds of liquefaction mitigation technologies. First, loose packing of sand particles is a cause of liquefaction. So we need to compact the grains. This is the first idea. Second one, falling or moving of particles into big voids. This story is changed by bonding or grouting of grains. Significant cyclic motion particles is reduced by mechanical constraint against ground motion. Long time is needed for drainage, so why don't you accelerate drainage procedure by installation of gravel drains, stone columns, by which, through which water can flow quickly towards the surface. Also, some people say incompressibility of water is a problem. So, okay, why don't you remove water from the ground? Well, why don't you inject gas bubbles into soil? So, by taking any one of the options here, you can mitigate the liquefaction hazard. So, mitigation measures for newly constructed structures by preventing liquefaction. For new constructions, actually, we don't have to worry about trouble by existing structure. There's no underground obstacles. Ground deformation, vibration, noise, etc. are allowed. There's no complaint in open space. So compaction, densification was the earliest technology to mitigate liquefaction. But we try to increase the standard penetration test M value to hopefully 20. So after compaction, now little pore water is drained out, liquefaction is unlikely, and the first technology of this type was bioflotations. Actually, in Dapronia, USA, started bioflotation technologies. But in those days, his target was not the earthquake problem. He tried to just improve static performance of sandy ground, and he was successful. And this technology was applied to earthquake problems in Japan in 1950s. It was 7 years before the Niigata earthquake, and it was quite successful. On your left-hand side, tank foundation was damaged because sand was not compacted, but on your right-hand side, fiber flotation successfully protected the tank. Then problem was heavy noise and vibration of the ground during fiber flotation or other kind of dynamic compactions. I remember that I was never able to communicate with colleague people within 30, 40 meters from compaction machines. Therefore, static type of machine was developed. No vibration, but machine rotates like this and moves back and forth in the vertical direction and push new sand, new material into loose sandy ground. Intrusion of new volume of sand means densification of original sandy ground. And this is just the idea of the vibration intensity. 20 decibel reduction is very, very possible. So nowadays we can easily talk with people within 5 meters from the machine. A good point of compaction is that no maintenance is necessary after ground improvement. You can just forget deterioration or aging or whatever. However, soil moves laterally because of this compaction. Therefore, soil movement may affect existing structures within, say, 5 meters. So we should avoid working compaction within, say, 1 meter. Anyhow, experience verifies the performance of technologies. So this is an example of static quiet compaction during 2011 Tohoku earthquakes. In one construction site near Tokyo, nearly 70% had been already compacted, 30% had not been. So you can easily recognize different performances. On your right-hand side, still there is water ejection from the ground. I mean, oops, too small. There's a pointer. This part. And now ecology is a very important issue in our world. So now in place of gravel or sand, now some companies try to push timbers into soil. This is an ongoing project near Tokyo. First, hole is drilled, then timber is pushed into soil, and top is just capped by bentonite powders. Actually, ideally, just we wish to drive timbers into ground. This is the easiest compaction. However, noise problem does not allow us to do driving. Dynamic driving is not allowed. Therefore, first we have to drill a hole like this by screws. Then we have to statically push timber into soil. This is more time consuming, but now environmental control is very, very strict against noise, construction noise. Local people hate it. But anyhow, timber is good for environmental protection. So consolidation, dynamic consolidation is another money-saving technologies. Already many years ago, French people verified that pressure meter data is increased by this dynamic compaction, dynamic consolidations. This is much cheaper because we don't have to push machine into the ground. Just surface is tamped by heavy weight of concrete. And this technology was verified as a good liquefaction mitigation technology during Chichi earthquake in Taiwan, 1999. This section was not yet compacted and the liquefaction happened. This section had been compacted, so no problem happened. And the SPT M value increased significantly like this. So now we can trust dynamic consolidation, but noise and vibration is the issue. So, so people used to love quiet technologies in early 90s. So grouting was developed. This is a mixing cement and sand by machine rotations. So in those days, 100% soil was mixed with cement. So this is quite expensive, but quiet, no vibration was produced. So this technology was accepted in developed urban area, but money was the problem. So as a cost-saving technologies, grouting in grid shape, grid configuration was developed also in early 90s. So now only grid part is mixed with soil, cement is mixed with soil there. So remaining part is just soil. So this is much cheaper. Only 30% of soil is mixed with cement. And this technology worked quite well during 1995 Kobe earthquake. There is hotel in Kobe Harbor, and in the surrounding area totally liquefied, but this building foundation was intact. No problem happened. So this is a photograph on your right-hand side during construction, installation of grid walls. So you can recognize that cement columns were installed and they are connected with each other and formed grid wall. Size is 5 meters, 7 meters, 10 meters, something like that. So what is the mechanism of this grid wall? Actually, cyclic shear is the procedure towards liquefaction. Greater shear strain means more chance of liquefaction. So idea is, why don't you decrease this shear strain by installing rigid wall like this. So actually this mechanism is different from that of 100% soil grouting anymore. This is constraining shear deformation. So most important issue in this technology is the wall interval. 30 years ago, Public Works Research Institute Japan did many model tests and decided that interval should be less than 70% of the thickness of liquefiable soil. So as an interpretation of model test, 70% was a good idea, reasonable, no problem. However, then practical people started to interpret this 70% rule in a different way. According to them, bigger design earthquake creates greater thickness of liquefaction from 3 meters to 10 meters. Then 70% of thickness also increases. Therefore, wall interval can increase during stronger, bigger design earthquake. This is nonsense. So nowadays, for practice, engineers carry out dynamic analysis, finite element analysis, nonlinear analysis in order to determine the wall interval. Then technology like this, premixing soil cement before reclamation. So this one worked quite well in 2003. Pile foundation is often attractive as a good, useful safe building foundations. In 2011, Tohoku earthquake, pile foundation successfully protected the building, but problem is consolidation settlement in the surrounding soil. After ejecting lots of groundwater, liquefied sandy ground subsided 30-40 centimeters. This means connection of lifelines for water, sewage, gas, electricity, communication are cut. So consequently, this building became useless. So for money saving, sometimes we allow for some limited extent of liquefaction, gravel drains or stone column is the most famous example. And soil is no more undrained and with these gravel drains. Water needs to travel horizontally by only 80 centimeters and quickly dissipated to the surface. So low effective stress 0, continues for only 5 seconds, 10 seconds. So during such a short time, ground cannot deform very much. So in this way, we can keep serviceability of structures. Also, this technology does not cause vibration, no noise. So near very humble wooden structures, we can do this technology. So this example after Kushiro earthquake 1993, this is my graph. And certainly subsidence happens because water is drained out, but this is small, only 10 centimeters, 15 centimeters. So we can easily repair this by overlaying asphalt at the surface. So this is not damage. Maybe some people are worrying about clogging effects. Silty sand may come into the gravel drains and closes the space. So afterwards, gravel drain does not work as a water channel anymore. So people were worried about this problem in 1980s. So full-scale shaking model tests were conducted. So you can compare the sand, the silt content in the horizontal direction. Gravel, this part, 0 centimeter to 20 centimeters. This is a part of gravel drains. So, and outside is just native sand. So, actually, what should I say? Sand content, so silt content did not change very much after shaking test. So we came to believe that migration of sandy, silty content is quite small or negligible. Only here we have just one, some increase. So, and the performance was very good in 2011 earthquake. Here, gravel drain was installed, so no damage happened to this river levee. But without gravel drains, big damage happened. And this is a cross section. There were many gravel drains like this. And this is a very important principle of earthquake resistant design of river levees. Flood and earthquake do not come together except near the sea. Near the sea, high tide means flood twice a year, twice a day. So we don't have to worry too much about deformation of levees caused by earthquake. We have some weeks, several weeks before flood comes. So we have time to repair the damage. So we don't need 100% safety for river levees. Quick restoration, maximum 2 weeks. This is the target of my government policy. So this is very, very possible if subsidence is less than 1 meter or maybe 2 meters. So we have this important empirical relationship from experiences from 1890 to 2011. Empirical relationship between levee height, H on your left-hand side, versus S, this is subsidence. So in the diagram, horizontal axis shows the original height, vertical axis shows the subsidence. So all data staying under this 75% line. This means in the worst case, 6 meter levee still keeps 1.5 meters height because maximum subsidence is never greater than 4.5 meters. So if this remaining 1.5 meters good enough to stop 2-week probability flood, then we have time to repair this levee for 2 weeks. So in this way, actually significant subsidence damage is still allowed from a probabilistic viewpoint. It's a pity for me that nowadays market share of drainage is decreasing. 1993, this much of share was occupied by the drain, but the share has been decreasing 11 years later, while other technology, densification, grouting, increased drastically. Why? Because in the design calculations, engineers want to keep effective stress in this part more than 50% of the initial value. This means water drainage should occur very, very quickly. So that's why interval between gravel drains, say only 1.5 meters. But after 1995 Kobe earthquake, actually design earthquake became even stronger. So design calculation of drainage or Darcy's law could not keep effective stress more than 50% anymore. So engineers, government engineers, officers actually gave up gravel drain technologies. But it's important that 2011 gravel drain still worked very well under this magnitude 9 strong earthquakes. Shaking here was 2 times stronger than design intensive motions. So actually this technology has something more than just drainage. I mean, gravel drains with good rigidity can keep the entire ground intact. This is mechanical reinforcement. But now current design principle does not think about this mechanical rigidity. Only Darcy's law is calculated. That's a problem. So human knowledge is still not enough to understand everything. And this is just the experience in 2011. House resting on liquefiable sandy layer becomes like this. Entire house sunk into subsoil. And Professor Asada studied house damage in 1980s, and he proposed that good thickness of H1. H1 means crust. No liquefaction happens here. If this H1 is good enough, big enough, house is protected. House does not undergo any damage, even if we have thick liquefaction soil, because of this punching failure mechanism. This red part, another red part, develop good shear resistance, and this is good enough to support the weight of light structure at the surface. So in line with this, after 2011, government decided to use this diagram as a guideline on house safety during liquefactions. So if H1 is greater than 5 meters, this ground is considered good, whatever liquefaction risk is here and in the lower layers. So in residential area, we try to achieve 5 meters, sometimes 3 meters as a target of surface compaction. Then after 3 meters or 5 meters, we can forget any problem underneath. So this is for money saving. Yes? Okay. So this is
Professor Tohata,
yes.
please wind up within 5 minutes.
5 minutes. Okay. So under existing structures, okay, 5 minutes. This is called compaction grouting, pushing grout into soil. And this machine is small enough to work in the basement. Machine is very small. And this is another type of injection of colloidal silica. This is expensive, but machine is also small. It can work in the oblique directions, so we can improve soil under existing structures. This is very important nowadays. And some people are worrying about aging effects of colloidal silica. They say after 10 years, 20 years, silica may be deteriorated. But no. If the material is good enough chemically, okay, this evidence, unconfined compression strength after 5 years, 10 years, 15, 20 years, kept intact. Also liquefaction resistance in the first 3 years like this, but after 10 years, it's maybe 2 times higher. So aging problem is not there. So now, okay, this is for technology for existing structures. I mean, river levees. Levee is deforms like this, but if we install sheet pile wall here, subsidence is reduced. So this is a practice. Okay, now sheet pile wall is installed along the foot of this slope. But problem is environment. Groundwater environment may be disturbed by this impervious steel pile. Therefore, holes are open like this. This is passage of waters. Also, floating of pipelines problems. So this is technology to stop the floating. So house is a most difficult target. In New Zealand, no improvement anymore. Relocation to safer place is a choice. But Japanese people don't want to move. They want to stay at the same place. So this house, okay, for this house, water was drained out like this. So dry soil, dry sand does not liquefy. So let me skip this one. Okay. Okay, this is ongoing drainage from a residential area. So this is successful. Also, this is also another project. Drainage pipe is installed here. So groundwater flows in horizontal direction and groundwater level goes down and surface 3 meters or 5 meters are made intact. My experience of this one, groundwater lowering may trigger consolidation in the soft underground, soft clay subsoil. Sometimes we have clay layer, sometimes sandy layer, but we have to improve entire residential areas. So groundwater lowering is not accepted in this area. As an alternative, we installed grid walls in vertical, horizontal directions like this. But this is very difficult because the space is so small, costly as well. So we did this. Let me skip this. So emerging topics. lifeline is actually a very difficult target because lifeline industries don't have enough money to improve the entire ground. Also, even those lifeline authorities are not allowed to touch the soil except in the backfill area. So this area is never enough to protect the lifeline system. So I propose this type of mechanism to prevent floating of pipeline like this. And another technology is installation of many columns to prevent big lateral flow. Blasting is another technology, but I failed to achieve SPTM value 20, only 18. Mixing with tire chips good. Kobe. So this is very interesting. Liquefaction occurred entirely in this island. And but in the central part, no liquefaction happened. But actually only this part, viable compaction. This blue part was intentionally improved against liquefaction. Other part was just installation of sand drain preloading for mitigation of consolidation problem. But during construction of sand drain preloading, heavy machines moved back and forth here, and it affected the density of surface soil. So consequently, no liquefaction happened. So this is unintentional mitigation of liquefaction. So miscellaneous. We need to find rich customers. Actually, house foundation was not a very good target because people don't want to spend much money. We wish to help people directly, but they don't want to be helped. This is a problem. So where is a rich future customer? This is my question. So time is okay. Many thanks for your attention. So this is the end of my presentation. Thank you very much to Pune.
Thank you, Professor Tohota, for a very nice lecture of practical importance. We are very grateful to hear a very nice lecture from you. Now, Dr. Krishnan, have you collected some questions?
Sir, I'm still waiting for the questions. Dear delegates, please feel free to type in any of your questions into the Q&A box in the 3D platform at the top left of your window. I have one, not a question, I have one comment saying that it's an excellent session. Of course, it was an excellent session, Professor Tohota. And I think we will have more questions coming in a few minutes. In the meantime, do we have any questions from the panelists? Do we have any questions? I don't think we have any questions as of now.
Okay. It's 10 p.m. in Tokyo.
May I ask one question?
Well, oh yes, please. Yes.
Thank you, Professor Gopal, for typing in the answers for all the questions that have been raised by the delegates.
That's okay. It's my pleasure.
Thank you, sir.
Somebody had a question.
Professor Swami Sharan, sir, over to you, sir.
Yes.
Yes, I think very nice. Both the presentations were excellent and very effective.
Yeah, actually. Okay.
The speakers very much.
Yeah. May I answer
Anything you want to convey, Professor Tohota?
So may I answer the second question? Yeah, second question addresses PARU, lateral flow during earthquake. First, I said that water leakage from unpaved canal just promoted the displacement, but it was the main trigger of a big flow because one site, Bararoa site, did not have an irrigation channel, but still big deformation happened. So what is the cause? Actually, I have been working for the research team under Japanese government, and the researchers proposed many ideas. One famous idea was water film formation. Water film. Water is drained out from liquefied sandy layer, but could not reach the surface because surface soil was less pervious. So water remained between surface soil and liquefied sand. So water had no shear resistance. So surface soil just flowed in the horizontal direction over 500 meters. This is very possible. Many shaking table tests, centrifuge tests verified this idea. But basic question is such a simple situation should have happened many times in the past. Actually, such a 500-meter big displacement never happened in the past. So this water film theory is too simple, too possible.
Professor Tawhat, I think
yes.
It's possible that the water film forms, but it's very difficult to sustain it for a long period of time because it will always find a way to drain.
Yeah. Water film flow lasted several minutes.
Yeah. So it can trigger the triggering event could be water film.
You are right. Yeah, you are right. Your point also important. So second idea, my idea was actually all lateral flow happened between big old alluvial fans. Alluvial fans are deposit from valleys. So alluvial fans all often include artesian water pressures. So my idea was strong shaking destroyed the underground aquifer, pressurized aquifer. So lots of water flowed into the slopes. So water was supplied into ground. So in this way, I was able to avoid the problem of sustainability, as you said. And another idea is actually, there are old faults under the slopes. This time, those faults did not move, but it's geologically possible that deep water, geological water, comes to the surface during earthquake. So this is another source of water supply. So basically, there are three ideas. We are fighting, academically fighting, but we could not reach any conclusions. So this was academic fighting for 2 years, but nobody won the game. So now I'm going. Another question.
Yeah, we have a few more questions.
Okay.
Sir, have you ever used diaphragms for liquefaction mitigation?
Okay, yeah. Any experimental evidence of performance of home mitigation? Yes. I already submitted several years ago to Soils and Foundation Journal. So if you want to know the reference information, please send me email. First author is Otsubo, but I'm certainly one of the authors. Then in one of the slides, there was one recommendation improving the soil only until 3 to 5 meters under the building. Can you share the reference for that recommendation? Oh, yes. Actually, Professor Ishihara, Kenji Ishihara, showed this idea in 1985 during International Conference Soil Mechanics Geotechnical Engineering in San Francisco. It was 36 years ago. If you need more information, please send me email. And please don't misunderstand that you can construct a heavy oil tank over 3 to 5 meter layer. No, tank is too heavy. I'm talking about just house.
So is there a recommendation on how much bearing pressure the structure should be limited to? Maybe 20, 30 kilopascals or something like that?
Yeah, something like that. 2 tons per square meter, something like that.
Yeah, that will be about 20.
Only. No,
yeah,
don't
20, 30
think
kilopascals.
about tank. And then next question. Can you please name few geological stones which can be mixed to avoid geological stones? Maybe this person, Mr. Wahid Shode, he means gravel drains or stone columns. If so, I would say mudstone is not good because mudstone becomes just mud after years. But sandstone may be okay. And then next question.
Tire chips.
Use sand tire clamps for liquefaction. Oh, yes. Actually, your colleague, Indian colleague, Professor Hazarika.
Hazarika,
Yeah, he loves tire tip technologies. I did only one time shaking table test to confirm the tire tip effects. But maybe nowadays Hazarika is a more suitable person to talk about this issue.
I think he'll probably will. He has a keynote lecture later on, so I'm sure it'll come up.
Yeah. Then, please. Oh, that's all. No?
That's all.
Yeah, thank you very much for your attention.
Okay. Thank you very much. Now we came to the end of the session. Now I am requesting to Professor Jaka if he wants to announce something.
On behalf of organizing committee, we thank both the keynote speakers, Professor Gopal Madhubushi and Professor Tohota, for kindly accepting our invitation and delivering today's excellent lectures. Thank you both. And I also thank, on behalf of organizing committee, our chair, Professor Swami Saran. In spite of technical difficulties, he managed very hard to attend our session and handle it. Thank you very much, sir. I also thank co-chair, Dr. Ramakrishnan, for effectively managing the session. Thank you one and all. And now there is, after a few minutes, grand cultural event is going to be start, and our colleagues, Dr. Parthasarathi and Dr. Srivalsa, made a lot of efforts for the cultural evening. So I request all of you to join and experience culture, Indian culture.